Good afternoon, everyone. Hope you are enjoying today and enjoyed the previous lecture in which we discussed about what are B trees. In this lecture, we're going to be discussing about basic operations on B trees. So, very simple operation is a search operation on a B tree. So, what essentially it is that given a node, this procedure or this algorithm will take given a node, and you want to find whether there is a key k exists in that node or not. So how we do that? It's very simple. That let's say it's similar to ordinary binary trees um, where you check each node whether the particular key belongs to the node or not. But in the case of B trees, it's essentially, since every node stores the keys in ascending order, and then that determines that basically the key may belong to which children or a subtree if the key is not found at an internal node. So what it is basically here, up to line number 1 to 3, that basically finds the smallest index I such that your key which you are trying to find belongs to is less than x dot key at a particular index, less than or equal to. Okay, so what it means that once you know that your key is less than particular index key, let's say k by I, and if your k key is not found here, then what you can do basically, you can descend to one of the subchildren. And so basically here is that if you find, then you return that particular node and the index I at which the key is found. But however, if it is not equal to, then if this is a leaf node, then you say key is not found. And if it is not a leaf node, then what it is, you recursively find the key k in the subchildren of that particular index x c I k, right? So basically what it is that so key acts as a separating as a separation of the subtrees. So you might have, let's say, if the a b, you have the children keys, and so what it is here, if you have c and e, okay, so now here you may have d, and you may have here f and g, and you are trying to find d, or you are trying to find basically b. So what it is that if you find that the b is less than or equal to c, so you just descend to the first children, and you will find the key here. Okay, so very simple algorithm. Now notice that what is the complexity of this algorithm would be, let's say if your height is h, then this algorithm will take O in big O notation th time, or you may also write it as O t log base t and n. That is the operation it will take, where n is the number of keys or your indexes at a particular internal node. Okay. Now let's talk about the creation of a tree. It's again a very simple procedure that once you know what you're going to store at each node, then you allocate the node, or in allocate node procedure, basically it is allocating the memory space. That memory space can be a page or can be just simple node or simple memory bytes, which a node typically will have. So node will have how many keys, whether it's a leaf node or not, true or false, a array structure or linked structure to store the values of the keys, and the pointers. So these are pointers to the children's. Okay. So remember, this key acts as the separating agent. So whatever are the children's, subchildren's of this tree, so the left subchildren, say KEYI, means that all the values, all the keys in this subchildren will be less than KEYI. Okay. And on the right subchildren will be more than KEYI. So that is the structure which is for B trees. So no matter what we do insertion or deletion, we have to preserve this structure. At every internal node, these keys are stored in a non-decreasing or increasing order. Okay. All right. So once you allocate that, you basically create a node, and once you allocate a node, you get the pointer to that particular node, and since the tree is empty, you just select that particular one node as a root node. Okay, simple process. Now insertion is a bit tricky operation. Okay, remember we discussed about what is T, is the order of the bit tree, and if the keys are stored at each internal node in an increasing order, and that order is maintained. So basically whatever are the subchildren's, so left subchildren of this tree, leftmost, will have all the keys less than key 0, and then the right children, next children, leftmost, and then the next children will have keys in between KY0 greater than KY0 and less than KY1. Okay, and next children will have KY0 greater than and less than KY1. Okay. So that's the structure is preserved. Now we have the case, interesting case, that if number of keys n is equal to 2t minus 1. What is the 2t? 2t minus 1 is the maximum keys this node can have. Okay. And if we want to insert another key at this node, how do we do that? So we have to first check if the number of keys stored at this internal node is equal to 2t minus 1, then we have to split that node. Otherwise, we just simply, node is not full, we can insert. Okay. So let's talk about how the splitting works. Okay. Before getting into the detailed algorithm. So let's say you have this y node. Okay, and you have this y node, and this node is full, means it has 2t minus 1 keys with the 2t its children. Okay, so what we're gonna do, we're gonna get its root node. Okay, this node's root node. Okay, let's say this structure is root node is this one. Okay, so how we gonna split it? So what we're gonna do, we're gonna find a median key. Okay, which is S here, the middle key, and move this middle onto the root, its subtree's root root key chain. Okay, at appropriate location. Okay, So let's say we have n and w, so s will fit between n and w. So we move s onto its parent node, and now this node is split into two nodes. So one will have PQR keys and another will have TUV. So the new node is split into two. Now these two becomes the children of its parent node, and how it's going to store that the keys, the the keys which are less than s will have pointer xci y equal to xci, and a new node, whatever number of keys which are greater than your s will go into the new children, and that new children will be added, so its pointer will be added to the parent node. Okay, so let's talk about the procedure. Okay, so it's a very simple procedure. That initially you say that whatever is the t to t dot root, you assign it to r, and one here line number 2 to 9, basically you are deciding here whether this this node in which you are going to insert this key, okay, is full. If it is full, then you have to create a new node. Okay, you have to create an extra, you have to split it, so it means that you are creating a new node which will essentially become another children. Okay, so that basically is doing that job, and then this procedure is splitting the child is nothing but the child of its parent is this one. So this node is getting splitted, and then you're going to insert this key k into the non-full node. So this becomes non-full node. Okay, new node. So now you're going to insert over here. Okay, otherwise if your node is not full, then you just execute non-full procedure. Okay, interesting enough. So now these two procedures, split child and no full, these are the key things which will determine the complexity of this algorithm. Okay, so remember, these procedures are recursive procedures. We discussed recursion in past lectures, and it's a very beautiful technique, recursive, doing the computation recursively. Write once and use that algorithm recursively based on different input sizes. All right. Okay, so now let's talk about the split child procedure first. So what it is, that the split child procedure, what it is, that it will take, say, node x and an index I such that x, okay, this node's children x dot c I for a corresponding index is full. Okay, is full. Okay, so what essentially it is that so its children was y is equal to x dot ci is full. Originally it will have 2t children's and 2t minus 1 keys. Okay, but now after splitting it will reduce to the t children and t minus 1 keys. Okay, so 2t children, 2t minus 1 keys. Okay, now it will reduce it to t children and t minus 1 keys. Okay, after splitting. Okay, so that one will become y and z will become similar way. You are splitting into 2 and t minus 1 keys. So line number 1 to 9, these line number 1 to 9 basically, these are creating a new node z, okay, and giving it the largest t minus 1 keys and corresponding children of y. Okay, very simple, line number 1 to 9. And then line number 10 is adjusting the key count for the original children, because now we have split it into 2 nodes, so we don't have those many children now in the original one. Now 11 to 17, that these 11 to 17, line 11 to 17, these are inserting this newly created children z okay into the x, which was the parent of the y. Okay, and also moving the median key to the keys of the x in order to separate y from z. Okay, and adjusting the x keys count. Okay. And now line number 18 to 20, basically these are writing the disk pages. Okay, these operations are writing to the disks the information which is changed for y, x, and z. So essentially, remember we discussed about that B trees are mainly used for secondary storage devices. That's why these operations are coming here. If you're going to write your own program, you may omit this. Okay. Now, how much time it's going to take this algorithm? Remember, we discussed about theta notations. Okay, big O notation. Sorry, I'm sorry. I misstated. Remember, we discussed about big O notations when we discussed about time complexity of an algorithm. So in this case, it's going to take theta h time. Okay. And all these disk operations going to take order of 1 time. Okay. Where t is nothing but the order of minimum order of the B tree. Okay. Now let's talk about insert no full. Okay, so when our node where we want to insert a key is full, then we have to split. After splitting, okay, after splitting we have a node which is not full, so we use this procedure no full at a node x and we want to insert the key k. Okay, so line number 3 is simple, that we're going to check whether that node is leaf node or not. If it is a leaf node, then we execute this procedure. If it is not leaf node, then we execute slightly different procedure. Okay, so if it is a leaf node, we just directly insert. We don't have to do anything much. We insert the key at the appropriate position. Okay, but if it is not a leaf node, if it is internal node, then what we do, we determine first which is the children of that intermediate node we want to insert. Okay, and we read that children's information. Okay, now same thing, after we read that information about that children, we need to know whether this children is full or not. If it is full, then we actually split the children, and after splitting we use the same routine recursively, right? Isn't it simple? Fascinating technique how to use recursions. Okay, now think about how much time this will take. Now this disk access to read the page, how much time is going to take? It's going to take whatever is the height of the tree. And how much this total whole process is going to take to insert a key at a node which is not full. Again, it's again simple, order of t, which is the minimum order of the tree, and the height h. Okay, we can also write it as t, h is nothing but log base t n n. All right. Okay, so we discussed about insertion procedure, creating the B tree, and searching. Now, deletion, how to delete a key from a B tree. This is a bit complicated and a tricky procedure. So we're gonna discuss in different cases. Let's say we have been given a tree, B tree, okay? This is the originally given B tree, all right? Now, case number 1, we want to delete a key f, okay, from a node, and this node is a leaf node, okay. So we just simply delete f, and after deleting f, we just left de the keys at this node. Very simple. Now let's talk about another case in which a key k is in the internal node. So we want to delete m, okay. We want to delete m, which is at internal node, and the child which precedes k, okay. The child which precedes k has at least t keys. Now we already said that we have this tree and minimum order is 3, so it has 3 keys. So what we're gonna do in this case, so we want to delete m, we have deleted m. Now after deleting m, we are left with 2 keys here, and so this is basically so moving disturbing the B tree property. So what we're gonna do, the child which is preceding this m, okay, the right most key or the greatest key L will take the place of the m. So we move m, L in place of m, and the resultant tree would look like this, okay. Now let's take another case. So in this case, what we did, we want to delete G, okay. So G, this is a case where K, the key is which we want to delete, is present in an internal node, okay, and the children Y and Z, both children have t minus 1 keys, okay. So what we're gonna do in that case, to preserve the B tree property also after deleting the key, what are we gonna do? We merge these two children, Y and Z. We merged and we removed this key, okay. Now let's talk about another case, okay. So don't go with the 3b or 3a. I'm discussing 3b first because I'm maintaining the consistency with the textbook, okay. Now 3b, we want to delete D, okay. So D, what it means that the key is not at this internal node but at the children, at the children node x dot ci at the particular index I, okay. Now x dot ci and both of x dot ci's siblings have t minus 1 keys, okay. So now what happens in this case, the recursion cannot go beyond this point because this C and L, it has only 2 keys. So to go recursion beyond that, we need more than 2. So what we're gonna do, we're gonna merge, we're gonna bring the key which is of its parent with this and merge CL with the TX. Okay, so we merged CL with TX and we wanted to delete D. Now we can delete D. D is gone. Okay, and resultant tree is like that. Now our root is empty. There is no key in the empty, so we can simply make a new root of the tree which is CLPTX. This node becomes the new root of the tree and the tree height is decreased by 1. Okay, now let's talk about another case 3a. Okay, now it is a similar case. We want to delete B. Okay, very similar case to the previous one with a little difference that the children has t minus 1 keys. Okay, x.ci has t minus 1 keys, but immediate sibling, so in the previous one immediate sibling is this one, has t keys, means three keys. Okay, so now what happens that when we want to delete B, okay, so the C which basically comes after this key, because this is the leftmost children in this case. So what happens, the C takes the place of B. B is gone and now this E takes the place of the C. Okay, and resultant tree will look like this. Okay, so guys, this was a quick video on basic operations of on B trees. If you want to implement these algorithms, I would recommend you to do so. You can take any programming language. Ideal would be the C or C++, and get your hands dirty. Thank you very much for watching this video. If you are struggling with algorithms, you may contact us for private lessons. Also, we would be happy if you subscribe LibProfessor channel on YouTube. This encourages us to create more interesting videos, and also do not forget to write your comments, which makes us to realize that okay, we did this mistake, we did that mistake, and help us to improve videos going forward. Have a wonderful day. Thank you once again.